Every single day, you use a simple machine that's, believe it or not, designed to make you weaker. Sounds crazy, right? But it sacrifices brute force for something way more valuable: incredible speed. Today, we're going to pull back the curtain on the third-class lever, the hidden speed multiplier that's all around you, and even inside you. Let's dive in. So let me ask you this. What could a simple pair of tweezers, a fishing rod, and your own arm possibly have in common? I mean, they seem totally different, but they all secretly run on the exact same brilliant engineering principle. And yeah, the answer is they're all levers. Now, at its heart, a lever is one of the simplest machines you can imagine. It's really just a stiff bar that pivots on a fixed point. We call that the fulcrum. You apply some force, and it moves a load. Easy enough. But, and this is the key, how you arrange those three parts, well, that changes absolutely everything. Which brings us to today's main event, the third-class lever. Other levers, like a crowbar, are famous for multiplying your strength. This one, it has a completely different job. It's all about speed. And its secret lies in a very specific arrangement: the fulcrum, the effort, and the load. Okay, so here's the unique setup. You've got the fulcrum, the pivot, at one end, and the load, the thing you want to move, is way over at the other end. But the effort, that's the force you apply, it goes right there in the middle. This FEL arrangement is the blueprint for how this whole thing works. So, let's just lock that in. Fulcrum, then effort, then load. FEL. That sequence is the non-negotiable signature of a third-class lever, and it's what leads to some really interesting consequences. Because that FEL arrangement forces a fundamental trade-off. See, in physics, you almost never get something for nothing. To get one big advantage, you usually have to give something else up. And with the third-class lever, you're making a very deliberate sacrifice to get its amazing benefit. And here's why it feels like you're working harder. The distance from the pivot, the fulcrum, to where you apply your effort is called the effort arm. And the distance from that same pivot to the load is the load arm. With this setup, your effort arm is always shorter than the load arm. You're basically at a mechanical disadvantage right from the get-go. We actually have a term for this. It's called mechanical advantage. It's really just a number that tells you how much a machine is multiplying your force. For a tool like a crowbar, that number could be 10, maybe 20. But for a third-class lever, the mechanical advantage is always less than 1. You're actually putting more force in than you're getting out. The source material we're looking at puts it pretty bluntly: a large effort is needed to overcome a small load. So, yeah, you are always fighting an uphill battle when it comes to force. Which, of course, brings up the big question, right? If this lever actually makes you weaker, why in the world would we ever use it? What's the point of a machine that makes the job harder, at least from a strength perspective? And this is the payoff. This is the whole reason it exists. You're not buying force. You're buying speed and a huge range of motion. Everything you lose in strength, you gain back in pure velocity. It's a trade for quickness. All right, so let's see how this trade-off actually looks out in the real world. Because once you know what to look for, you start seeing these amazing speed multipliers absolutely everywhere. Our source text gives us some classic examples. Things like coal tongs or tweezers, where you squeeze right in the middle. A fishing rod, where you lift up between your hands. Or even a broom. Your top hand is the fulcrum, and your bottom hand provides that effort in the middle. Just think about a pair of tongs for a second. Your fingers only have to move a tiny bit, just a small squeeze. But in that exact same moment, the tips of the tongs travel a much bigger distance. That right there is the speed multiplication. A small, slow input creates a big, fast output. But maybe the most incredible example of a third-class lever isn't something you hold. It's actually part of you. Your body is just full of these amazing built-in speed systems. The human arm is probably the perfect example. Your elbow acts as the fulcrum. Your bicep muscle attaches to your forearm just a little bit past the elbow. That's your effort. And the load? Well, that's whatever you're holding in your hand. Fulcrum, effort, load. It's a perfect third-class lever. And this is the truly incredible result. Your bicep only needs to contract a couple of inches, but that small, powerful movement slings your hand through this huge arc, and it does it super fast. It's the whole reason you can throw a ball so quickly or swing a tennis racket with so much velocity. You're trading strength for speed, all thanks to the lever built right into your own body. So next time you pick up some chopsticks, swing a golf club, or even just wave goodbye, you're tapping into this amazing principle. You're trading force for speed. So I'll just leave you with this question. Now that you know what to look for, what other hidden speed multipliers are you going to spot in your daily life?
This is the brief on third-class levers. So, if you're an engineering student or just a naturally curious mind, we're diving into a really cool concept today, where a simple machine is actually designed not to multiply raw force, but instead to completely maximize your speed and range of motion. First off, let's break down the actual physical setup. In a third-class lever, the effort, your input force, is located right in the middle, sitting directly between the fulcrum, or the pivot point, and the load you're trying to move. Second, let's talk about the mechanical trade-off here. Because the effort arm is shorter than the load arm, the mechanical advantage is literally always less than 1. So, what does that actually mean? Well, it means you have to apply a larger effort to move a smaller load. But hey, the massive payoff is that the lever dramatically increases both the speed and the distance that the load travels. Finally, we see this all the time in real life. You're using this exact mechanic probably without even noticing when you grab a pair of tongs, sweep with a broom, cast a fishing rod, or honestly even when you just flex your own arm muscles. To bring it all together, third-class levers purposefully sacrifice lifting power in exchange for a huge boost in speed and distance. Because, sometimes in engineering, having lightning-fast reach is just way more valuable than having sheer brute strength.